we are going to start limits. So let's start with this following example. Let's say you were asked to solve 2 times cosine x plus sine 2x is equal to 0. So basically you want to find all values of x for which the equation is true. And how do we do that? Well, you look at this equation and you have no idea what to do. In trigonometry, often when you have no idea how to proceed, you look for identities that you can apply. Okay? So here you see that you have double angle for sine. So that tells you let's try applying the double angle formula for sine. So let's see what happens if I have 2 cosine x plus 2 times sine x cosine x. So this quantity here is the same as this quantity here, and we know that from the double angle identity. Now you can see that we can factor out a 2. We can also factor out cosine x. And if I do that, I am going to get 1 plus sine x. You guys agree with that? Okay, now we basically have the product of 2 factors, right? I have 2 factors here, and the product is 0, so one or the other one is 0. So that tells me either 2 times cosine x is 0, or 1 plus sine x is 0, which means that either cosine x is 0 or sine x is -1. Is everybody okay with that? Well, first of all, let's look at cosine x equals to 0. Can you give me an angle? Well, give me all the angles between 0 and 2 pi where cosine x is 0. Yes, very good. So when x is pi over 2, when you get the angle pi over 2, the terminal side, remember the unit circle, the terminal side will be on the positive y-axis. And what's the intersection of the unit circle with the positive y-axis? The point 0, 1, and the first coordinate is 0, so cosine of 90 is 0. And also, as you said, when the angle is 3 pi over 2, then the terminal side of the angle is the negative y-axis. So the intersection of the negative y-axis with the unit circle is the point 0, -1. Still the first coordinate is 0, so cosine is 0 there as well. Now these are the only 2 angles between 0 and 2 pi where cosine is 0. Now what are the other angles? Well, there are many other angles which are coterminal with these 2 angles, right? So can you describe all the angles which are coterminal with these 2 angles? Well, all I have to do really is add a multiple of 2 pi. If I add a multiple of 2 pi to both of them, then I get all the angles whose terminal sides will be either the positive y-axis or the negative y-axis. So here, what is n? Here n represents a integer, so it could be 0, plus or minus 1, plus or minus 2, and so on. It's an integer. So these are all the solutions. There are infinitely many of them. Is everybody okay with that? Is that okay? Now, another way of expressing this same solution would be the following. Now, I can also express this solution by saying, notice that whenever I get an odd multiple of pi over 2, I am either on the positive y-axis or the negative y-axis. You agree with that? If I have an odd multiple of pi over 2, so a 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, right? Odd multiples of pi over 2, or negative 9 pi over 2, negative 7 pi over 2. So odd multiples of pi over 2. So I want to write pi over 2 and multiply that by an odd number. And generally we can express an odd number by writing 2n plus 1. Here again, n could be any integer. So that's another way of expressing the same solutions. Okay, you know, this is equivalent to writing this, because all we want is the odd multiples of pi over 2. Yeah.
Would that answer work on
In WebAssign, they usually ask you to give specific values between 0 and 2 pi. Yeah. They usually don't ask you to give all the solutions. Yeah. And usually if they expect some answers like this, they usually give you multiple choice, so you just have to pick. So that way there wouldn't be any problem recognizing the answers. Okay, we are not done yet. This is half the story. Then I have sine x equals to negative 1, right? So that tells me x is what? Well, where could sine x be negative? Sine x is negative. Sine x is the second coordinates of the points on the unit circle. And the only place on the unit circle where the second coordinate is negative 1 is at 3 pi over 2 angle, right? So x could be 3 pi over 2. And between 0 and 2 pi, that's the only angle where sine x is negative 1. You realize that? Because there is only one point where the second coordinate is negative 1, right? And that's where you have 3 pi over 2. And notice, and then if I want all the angles coterminal to 3 pi over 2, I have to add a multiple of 2 pi. That's it. Right? Again, n represents an integer again. So once I find one angle between 0 and 2 pi, I have to add a multiple of 2 pi to describe all the angles, all the solutions, okay, which are coterminal to this one. So they will all be solutions. Is that making sense? Okay. So this is it for for examples from trigonometry, but I haven't really reviewed the graphs of trig functions. Okay. At this moment, I am sort of forcing myself to stop reviewing and start doing calculus. However, if you don't remember the graphs of these trig functions and so on, you can review from Appendix D, as well as one of my videos in Moodle has that as well. So if you want to review that, that's fine. Again, at this point, it is a very good idea to go over all the exercises in Appendix D. Make sure you can do them, and make sure you are good with, you make friends with trigonometry from now on, so that whenever you have to use them, you can call on them and use them, okay? So what I want to do now is simply move to what I want to do today. So what I want to do today is move to, I think this is section 1.5. So this is going to be on limits. And this concept of limit is what makes calculus different from anything else you have seen in high school math, right? This concept of limit, it allows us to deal with infinity in an effective way. Okay, in algebra or other courses, you never used infinity, right? So in calculus is where you can effectively use effectively talk about infinity by using limits. And before I tell you what do we mean by limits, I want to give you some motivation examples to see that this idea of limit is not some guy just made it up to do just mathematics. It actually came out of problems in physics and other places. So some motivation examples for limits. Okay, so first of all, some motivation. Examples. My first motivation example would be the following. Let's consider. So example 1. Let's consider the function y equals to t squared. So this is basically the parabola. So. And let's sketch the graph of this function. Okay, let me draw my x and y axis. Okay, and I have to be a little bit careful how I draw this graph so that I can make my picture nice. Let me try to draw this. That's fine. The harder part is making the other half of it. Looks symmetric enough. Okay, so I guess it's good enough. You get the idea. That's what I say when I can't make a nice graph. Okay, so here's what I want to do. Let's pick a point here. Usually, so what I want to do is talk about tangents, like slopes of tangent lines. And in geometry, when you in analytic geometry, how did you define tangent? What definition of a tangent line did you take for a circle? We say that a line is tangent to a circle if it touches the circle at one point only, right? Well, that's nice and good for circles, but it really doesn't work for a general curve. Let's see why. Suppose that I have the following a curve. Let me try to make the. Suppose I have a curve like this, and then I have this point here, and then I'm going to make a tangent line here. Notice that tangent line at this point P may intersect the curve somewhere else, right? So the definition that it touches the curve at one point only doesn't work in general for any curve. Okay, so what is a tangent line intuitively? Well, intuitively, the meaning of a tangent line is the following. If I pick a point on the curve And then if I pick a very small portion of the curve, okay, near that point, then that portion should look like points on that portion should line up on a straight line. Am I making sense? The smaller portion you pick, the closer that portion will be to a line, right? That's intuitively the tangent line. Compare that with the following situation. If I have a curve, and this is the point which is a sharp point on the curve, notice that no matter how small portion I pick on either centered at that point, right? There are always points which make a triangle, right? Am I making sense? So they don't line up on a straight line. No matter how small I pick, it doesn't get closer and closer to a line. That portion doesn't get closer and closer to a line. So in this situation, I would say that, well, there is no tangent at that point. In the other case, I'll say that there is a tangent. Okay? So that's just intuitively what's the tangent line. Now, the problem that I want to look at is the following one, which is I have this parabola, and I want to know what's the slope of the tangent at the point, let's say 1. So when x is 1, what is okay, so when x is 1, what is the y value? 1, because it's the parabola y equals to t squared. I'm not xt. When t is 1, y is 1, and so this is the point 1, 1, right? This is the point 1, 1, and I want to know what's the slope of the tangent at this point. So how do I come up with that? Well, what we are going to do is pick an arbitrary point. Pick an arbitrary point on the curve. So for any t. So let's pick this point here. In order to make my picture clear, I have to do a little bit of work here. Okay, and I'm going to take an arbitrary point here, and the x coordinate of that point will be denoted by t. Then what would be the second coordinate of this point? Would be t squared, right? Because it's the graph of t squared. And then I am going to take a straight line joining these 2 points. So Okay, so that's the straight line joining these 2 points, let's say, and I'm going to label this point as P, label this point as Q, and we want to know what is the slope of the tangent at this point. Okay, so the question is, what is the slope? What is the slope of the tangent line at Q, and as well as what does it mean to say that there is a tangent line at 1, 1? What does it mean to say there is a tangent line? Well, first of all, what you want to realize, t could be on the other side of 1 as well. So if t is, maybe t is here, okay? Maybe t is here. So in that case, you get this line segment. So maybe p, location of p is here. So what I'm saying, p is an arbitrary point on the graph, okay? It could be on the left side of 1, it could be on the right side of 1. Either case, Can someone tell me what is the slope of the line segment from P to Q? What is the slope of the line segment from P to Q? So what's the slope of the line segment joining P and Q? And I'm going to denote this by m of t, okay? So m of t will denote the slope between the point P and Q. And what is that slope? Yeah. Yeah, it's basically rise over run. You know the coordinates of both points, and one of them is 1, 1, the other one is t squared. So you rise over run, so you subtract the y coordinates, subtract the x coordinates. So if you do that, you get t squared minus 1 divided by t minus 1. Now, notice one thing here. Can I say the following? Now, let's let t to approach 1, okay? So let's allow t to approach 1. So t gets closer and closer to 1. What's happening to the line segment? What's happening to the line segment PQ? Let me draw the tangent line here. So let's say the red one is the tangent line. So as t approaches 1, the line segment PQ, right? What is happening to Q? Q is approaching P, right? Q is approaching P, and so the line segment PQ is approaching to what? What? No, the line segment PQ. So what I'm saying is, so suppose that the new location of P, let me try to make another line segment here. So here's another point. So here's P when t is even closer, right? My point is, when t gets closer and closer to 1, P is getting closer and closer to Q, and as such you have that the line segment PQ is getting closer and closer to the tangent line, right? Okay, so that's the idea. So that means that as t approaches 1, the slope of PQ should be approaching the slope of the tangent, right? Am I making sense? So let me write that down. So as t gets closer and closer to 1, okay, the line segment PQ gets closer and closer to the tangent line t. Let me label the tangent line. Let me label the tangent line by t. And so PQ approaches t, and so the slope m of t of PQ, which is given by this, should approach the slope of t, right? Slope of t. So basically what I'm saying is that as t approaches 1, if the ratio t squared minus 1 over t minus 1, if that ratio approaches the number like 2, right, then I'm saying 2 should be the slope of t. Am I making sense? So that ratio is the slope of PQ, and as t approaches 1, PQ goes to the tangent. So as t goes to 1, if the ratio goes to 2, then 2 should be the slope of that tangent. Okay? Is that making sense? So the question is then, does this ratio, as t goes to 1, does this ratio or the slope of PQ, does that slope approach a specific number? Okay, like 2. How do I know that? Well, how about the value of the ratio at 1? Well, the problem is the ratio is undefined at 1. So when t is exactly 1, the ratio is not even defined. So, but I still want to know when t is close to 1, is the ratio close to another number? Okay, so how do I decide that? Well, so now we study this slope function t squared minus 1 over t minus 1. And can we come up with the graph of this function? Sure, right? We did an example like this before. We see that we can factor out the numerator in this way. And then we get t plus 1. So what's the difference between this function and this function? They are the same except at 1, right? So what's the graph? Well, the graph looks like the following. What's the graph of t plus 1? If this is 1, this is 1, then the graph looks like this is the graph of this line is the graph of t plus 1, right? You guys agree with that? Now, when t is 1, right, this is the t-axis, this is the y-axis. When no, not the y-axis, I guess I'm using m. So maybe write m here. What is the value of the function at 1? That's 2, right? T plus 1. When t is 1, t plus 1 is 2. However, what's the graph of the ratio when t is 1? It has a hole, right? So this would be the graph of t squared minus 1 over t minus 1. Okay? It's the same as the graph of t plus 1, except at 1 you have a hole. Now let's study what's going on when t is close to 1, right? Is it clear that when t is close to 1, the value of the slope function, the ratio is close to what? 2. Okay? So that tells me that the slope of the tangent at the point 1, 1 for the parabola should be 2. Okay? Am I making sense? So what does it mean to say that? What does it mean to say that I have a tangent line at the point 1, 1? I can say that we have a tangent line at the point 1, 1 if the slope function t squared minus 1 over t minus 1, that slope function gets closer and closer to a number when t gets closer and closer to 1. If that's the case, then I have a tangent line. If that's not the case, then I wouldn't have a tangent line. Am I making sense? I'll show you some certain examples later to explain that. But right now I'm saying at a point on the curve I have a tangent line if whatever the slope function is at that point, like this, t squared minus 1 over t minus 1, if that slope function approaches a number when t approaches 1. Is that making sense? And what's the slope? Well, the slope is given by the limit of this ratio as t goes to 1. So because we see that t squared minus 1 over t minus 1 is close to 2, when t is close to 1, we write that the limit as t goes to 1 of t squared minus 1 over t minus 1 is equal to 2. Notice that the ratio is not even defined at 1, right? The ratio is not defined at 1, but we are saying that the limit of the ratio is 2. That is, when as t gets closer and closer to 1, the ratio is getting closer and closer to 2. Okay? And basically then the slope is given by this number, the limit of this slope function. Is everybody okay with that? However, there is a sort of a problem here with what I'm saying, which is what I'm saying is that when t is close to 1, so when I say the limit of this function is 2, all I'm saying is that when t is close to 1, the ratio is close to 2, right? Now, is that a good definition of limit? Saying that the limit of this function is 2 means when t is close to 1, this guy is close to 2. What is the problem with that, saying that? Well, then you can say, hey, what do you mean by close to 2? How close to 2? How much close to 2? You have to clarify that. How close to 2? Well, so what it means to say that, so this, when I'm writing this, what it means precisely is the following. The value of this ratio can be made as close to 2 as we, how close to 2? Well, as close to 2 as you want to, as close to 2 as we desire. By taking any t in a suitable open interval centered at 1, except possibly equal to 1. Because when you take t to be equal to 1, the function is not even defined, so there is nothing to say. But we don't care what happens exactly at 1. What we care is what happens when t gets closer and closer to 1. And what we are saying, we can make the ratio as close to 2 as I want to, simply by taking any t in a small enough interval centered at 1. In other words, if I have a number line here, let's take another number line here. Here's another number line. And let's say here is the number 2. And then suppose that one of you give me a very, very small number, your whatever small number you desire. Say someone says, well, 0.001. So you want the value of the ratio to be between within 0.001 of 2. 0.001 of 2. So you want the ratio, the value of the ratio, to be within 0.001 of 2. Can I do that? Can I accomplish that by taking any t in a suitable small interval centered at 1? So can you find a very small interval centered at 1 such that whenever t is there, the ratio is within 0.001 of 2? If you could do that, then the limit is 2. Otherwise, the limit is not 2. Now, somebody else might desire 0.0001 instead of 0.01. That means I want the ratio to be even closer to 2. Can I do that? Well, maybe I have to pick a smaller interval centered at 1 in order to accomplish that. Am I making sense? So again, I can make the value of f of the ratio as close to t as I desire simply by taking any t in an open interval centered at 1, except possibly equal to 1. We don't care what happens at 1. If I can accomplish that, then the limit is 2. Otherwise, the limit is not 2. Now, when you look at this precise meaning of limit for the first time, sometimes it doesn't sink in right away. So you just have to look at this definition a couple of times, think about it, and see what it means. Okay, and it's gonna, at some point it's gonna make sense, if not sooner. Again, why is this definition meaning so difficult? Well, just to give you an idea why this is difficult, people have been using limits for a long time. Thousands of years back, people started using the limits. They had been computing limits of functions, all types of functions. But they didn't have a precise definition of limit for many years, like a couple of hundred years, they didn't have a precise meaning of limits. So somebody finally came up with the precise definition of limit, and so you can see why this concept could be a little difficult to grasp. But as you do more and more examples and limits and so on, it's going to get easier and easier. So again, my goal in this example was to show you that the concept of limit of a function is not something somebody made up in math and then some people found out usefulness of it. It's the other way around. Concepts in physics led us to consider this type of ideas. So the idea of limit came from this type of idea of finding the slope of a tangent. There is another example which you can relate to even more, which is the following. Let's say I have a real number line, and I have let's say this is the origin, and let's say I have a bug moving along this curve. So I have a bug moving along this curve, and the position of the bug at time t, let's say, is given by p of t, and the p of t is t squared. So I'm saying the position of the bug at time t is the square of that time. Okay? And let's say at time 1, what would be the position of the bug? At time 1, the position of the bug would be 1, right? So again, the bug is moving along this curve, along this line. And the question that we want to ask then is the following. I want to know what's the meaning of instantaneous velocity at time 1? What does it mean to say that the instantaneous velocity is something at time 1? Right? If you go from here to Columbus, let's say in a straight line, it takes you, let's say, 2 hours, and the distance is 70 miles, right? Average velocity makes sense pretty easy, right? Average velocity is just 70 divided by 2, right? Total distance divided by time, that's the average velocity. But what does it mean to say that at some point in time, your instantaneous velocity was 40 miles per hour, right? So what does it mean to say that? Well, so think about this bug then, and can someone tell me what's the average velocity of this bug over the time interval from hour 1 up to hour t? So what is the average? What is the average velocity over the time interval from 1 to t? What is that? T plus 1 over 2? No. Yeah. Okay, you are using calculus. You're not allowed to use calculus. You are telling me, what you're telling me there is the instantaneous velocity, okay? What I'm looking for is the average velocity over this time interval. In physics, how do you define average velocity? It's the net distance or net displacement over the length of time, right? So, yeah, so it's the position at time t minus the position at time 1. So that's the net displacement divided by the length of time is t minus 1. In other words, this is t squared minus 1 divided by t minus 1. I'm just recycling my same function. Okay. Notice that this is what happens when t is larger than 1, when time t is larger than 1. What if t is smaller than 1? What would be the average velocity? So in this case, t is larger than 1. What if t is smaller than 1? So then t would be like the interval, time interval would be like this. And then it would be p of 1 minus p of t, right? Position at the later time minus the position at the beginning time. And then 1 minus t, sorry. It will be 1 minus t here, which would be what? 1 minus t squared over 1 minus t. Are they the same? They are actually the same. The two ratios are the same because of what? You know, in the numerator I can flip them, in the denominator I can flip them, and then it becomes the same, right? I am allowed to flip both. If I flip both the terms in the numerator and both terms in the denominator, I'm not changing anything, right? You agree with that? Basically, I am multiplying the numerator by -1, multiplying the denominator by -1, and you see that they are actually the same. They are actually the same. So either way, I see that the average velocity, whether time is less than t is less than 1 or bigger than 1, the average velocity over that time interval is given by that ratio. So then, what's the instantaneous velocity at time 1? Well, what do we know about this? We already seen this ratio before. We said that when t is close to 1, this ratio, which is now the average velocity over the time interval from 1 to t, and that one is getting closer and closer to 2, right? So what is happening? I am fixing the time 1, and then I'm allowing time t to approach 1. That is, I am shrinking the time interval to 1. I'm shrinking the time interval toward 1, and then the average velocity is approaching the number 2, right? As I shrink the length of time, the average velocity is approaching the number 2, right? And I'm shrinking the time toward 1. So the instantaneous velocity at time 1 should be 2. Okay? So this should be the instantaneous velocity at time 1. Okay? Is that making sense? Okay. So once again, what it means to say that the ratio approaches 2, more precisely, is that I can make the value of the average velocity being the ratio, I can make the average velocity as close to 2 as I want to by picking time close enough to 1. Okay? By picking any time close enough to 1, I can make that average velocity as close to 2 as I want to. And because of that, 2 should be the instantaneous velocity. Okay, so so these are the two sort of motivation examples, in the sense that you can see where the concept of limits came from. So next time what I want to do is write down the definition of the limit of a function, and then I know a lot of you who have taken calculus, you might be asking, when are you going to show me how to compute limits easy ways? We're going to do that also.